Good morning, everyone. My name is Pranay. I'm from CSC AML Section C. Today, my subject Basic Electrical and Electronics Engineering. So, in my Basic Electrical and Electronics Engineering, my topic is self-inductance and mutual inductance. First of all, inductance is an important concept in electromagnetism as well as electrical engineering. This inductance explains how electric current changes, creating magnetic field and inducing a voltage. Next, there are two main types of inductance as we discussed, self-inductance and mutual inductance. These principles are widely used in electrical devices such as transformers, generators and inductors. Now, let us start about one of our topic. The one of our topic is self-inductance. So the self-inductance, it is a property of a coil or it is a property of a conductor by which a change in current flowing through it induces an electromotive force, that is EMF, in the same coil. This induced EMF, it opposes the change in current according to Lenz's law. Now, the induced EMF in the coil due to self-inductance, it is given by E is equal to minus L into di by dt, where E is equal to induced electromotive force, L is equal to self-inductance of the coil, di by dt. This di by dt is nothing but rate of change of current. The rate of change of current is nothing but di by dt. L is called self-inductance of the coil, E is called induced electromotive force, and the formula is given by E is equal to minus L into di by dt. Now, what is the unit of inductance? As we know, it is Henry. It is named after the scientist Joseph Henry. So, the SI unit, that is SI unit of inductance, is Henry. Now, let us take a simple example where self-inductance occurs in an electromagnetic coil. Now, a simple inductance of self-inductance occur in electromagnetic coil. When the current through the coil changes, the magnetic field around the it changes, inducing a change or a flux change or inducing a EMF in the same coil. Now, let us talk about one of our other topic, that is mutual inductance. The mutual inductance is the phenomena in which a change in current in one coil induces an electromotive force in a nearby coil. So it is the phenomena in which change in one current coil induces EMF in a nearby coil. So this is the property of mutual inductance. So change in one coil induces change in other coil. Right. Change in one coil, change of current in one coil induces EMF in nearby coil. This occurs due to the changing magnetic field produces one coil links with another coil. The induced EMF in the second coil, it is given by E is equal to minus dm into minus di by dt, minus m into di by dt. E is equal to minus m into di by dt. E is equal to induced electromotive force in the coil. M is mutual inductance between the coil A and coil B or between the any two coils. Di by dt is nothing but rate of change of current in the first coil. Here E is the electromotive force in second coil because we have taken second coil, right? Right. Since two coils are taken here. The unit of mutual inductance is also Henry. It is named after the scientist Henry. The most common application of mutual inductance is transformer. A changing current in the primary coil produces changing magnetic field which induces voltage in the secondary coil. Now let us start talking about the factors that affect our inductance. So there are several factors that influence or that affect our inductance, but the amount of inductance in a coil depends upon several physical and electrical parameters. Understanding these factors helps engineers to design efficient electrical devices. The first factor that is affecting our inductance is number of turns in the coil. The inductance of a coil increases with number of turns of wire. As the number of turns of wire is more, the inductance of coil is more. As the number of turns of wire is less, the inductance of coil is less. The inductance decreases with the decrease in number of turns of wire, and the inductance increases with an increasing number of turns. So, more turn produces a strong electromagnetic field, and low turns, small turns or minimum turns, it produces minimum or weak electromagnetic field. So strong electromagnetic field increases the magnetic flux which is linking the coil, whereas weak electromagnetic field, it cannot increase or it decreases the magnetic flux that is linking to the coil. So here we can say that inductance is directly proportional to the square of number of turns, as we have seen a formula NIA square. NIA square. So we can see that it is proportional to the number of turns. Now let us talk about the area of coil. The cross-sectional area of coil also, it affects the inductance. Larger coil area allows more magnetic flux through pass it. So more area, more will be the inductance. Less area, less magnetic field flux will be passing through it. So this increases or decreases, it decreases the inductance. Whereas in case of cross-sectional area, as the cross-sectional area is the more, the inductance is more. As the cross-sectional area is less, the inductance is less. Now let us talk about the length of the coil. When we talk about the length of the coil, the inductance, it increases as the length of coil decreases. Why? Because a longer coil spreads the magnetic field over a large region. This increases or decreases magnetic flux density. So longer coil spreads the magnetic field over a large region. This reduces the magnetic flux density. Magnetic core material. This type of material is placed inside the coil, greatly influences inductance. Example, air core, iron core, ferrite core. So this material with high magnetic permeability, they increase the magnetic field strength, and therefore they increase the inductance. So the distance between coils for mutual inductance, in case of distance of mutual inductance, the distance between the coil is very important. If the coils are closer together, more magnetic flux will be produced from the first coil links with the second coil. Whereas if the coils are far apart, magnetic coupling becomes very difficult and it becomes one of the weaker section. Now let us start talking about applications of self-inductance and mutual inductance. So in our daily life, there are many in modern electrical and electronic systems, there are more usage of self and mutual inductance. Now let us see. First is transformers. Transformers operate on the principle of mutual inductance. They transfer electrical energy from one circuit to the another through a changing magnetic field. Transformers are also used in power transmission, electrical distribution systems, electronic devices. Inductors. Inductors store energy in the form of a magnetic field. They are used in filters, power supplies, electronic circuits. Okay. Now, when we start talking about importance in modern technologies like electric toothbrushes, electric vehicles, these are some applications. Now, importance in modern technologies, inductance, it also plays an important role in many technological fields, especially in electromagnetism and electrical engineering. It helps in controlling the current changes in circuits, storing the magnetic energy, transmitting the electrical power efficiently, designing communication systems better. Without inductance, many modern electrical devices, they would not function properly. So I would like to conclude this topic saying that self-inductance and mutual inductance, these two are fundamental concepts that are involved in our electromagnetism. These are fundamental composites or components in our electromagnetism. Self-inductance occurs when a changing current in a coil produces EMF in the same coil, while mutual inductance occurs when a changing current in one coil induces EMF in another coil. These principles form the basis for many electrical technologies such as transformers, motors, inductors, wireless power transfer systems. Understanding inductance helps engineering design efficient electrical devices and improve modern engineering technologies. With this, I would like to conclude my topic, and I would like to thank each and everyone for giving me this opportunity. Thank you.